This final lecture is going to be about science and how it is that we come to know about the world. Science is almost certainly our greatest tool for achieving knowledge about reality. It's made our lives considerably easier over the centuries. It's helped us to live longer and to be healthier. It's gotten us into space and the deepest parts of the ocean. Yet it has also led to atrocities, things like nuclear warfare and chemical weapons attacks. What exactly is science? There are two uses of the word science that often get bandied about. The first, and probably the most common use of science, is when we appeal to some collection or body of knowledge. We claim that something is proved by science or shown in science. And that tends to be sort of like we're just referring to this collection out there as if it's its own thing. But this use of the word is a little bit tricky because it's unclear from the way that we use it how this body of knowledge came to be, how we got this body of knowledge, where it came from, and what exactly makes it different from, bodies of knowledge that are involved in the making of art, like basket weaving, or the bodies of knowledge involved in religious teachings when someone is preaching from the pulpit or teaching you in Sunday school. And what makes science different, what makes this collection of knowledge different, is the second use of the term, which incorporates or sort of involves a method. Science ultimately is a method of investigation, and that method kind of helps to, we can understand it as leading to this collection of knowledge. What science involves, in the sort of classical sense of what we're talking about, is empirical methods of testing and experimentation. That empirical methods involve the use of our senses. To answer the question of where this knowledge comes from, science, the sort of using this method, we are able to glean this knowledge by interacting with our world under controlled situations in attempts to experiment and test. And what makes science different from sort of, the knowledge gained in arts and crafts and religious teachings is the method of science and its purpose. The way that science is brought about, the way that it's enacted, and the thing for which science is attempting to achieve, the truth about reality. Have you ever been tempted to think that everything that's true, all the facts in the world, will eventually or ultimately be found out by science through the method of science? I know I have. Sadly, this is not the case. At least with the limitations we currently have as humans, there's a whole number of things that science could in principle discover, but that we will never or are ultimately unable to test because we don't have the resources for experimentation. For instance, this is an image of the Large Hadron Collider, which helps us to know about quarks and subatomic particles. In order to ultimately run bigger and better tests for determining the kinds of subatomic particles that they are, we would actually need a collider the size of Texas that would have to live somewhere out in space. That currently is something that we cannot possibly put together. There are also, though, a number of things that science simply isn't in the business of discovering or learning about, that lay at the very foundations of what science is. Science itself as a method simply isn't well positioned to investigate some of its foundational assumptions. Now, in order to undertake the sort of empirical methods that we follow in science, we have to use our senses and we have to use our perceptual systems in order to see and understand what's going on out in the world. We have to observe the results of our experiments and our tests to determine what, if anything, is actually happening out in reality. But as we've seen in previous lectures, our perceptual system can be fooled. We can fall victim to the constancies that we use when they're put into funny situations when it comes to seeing and hearing. In the case of like optical illusions or like the McGurk effect. So we can't always trust what it is that we see to be accurate. That is, that we can't trust the sort of representations of our visual perceptual systems to always be genuinely accurate representations of reality. Now, if you remember back to previous lecture in the discussion of the difference between seeming and being, I argued that in order to understand what it is for something to seem to be some way, we have to already understand what it would be for that thing to actually be that way. That is, if you're thinking about what it would be, what it would be like for the ball to seem to be red, you have to already understand what it would be like for the ball to actually be red, right? But what does it mean for something to be any way at all? And how can we ever really know whether anything out there is actually the way that it is, rather than just the way that it seems to us? The question comes, is our knowledge of the world really knowledge of the way that the world is? Or is our knowledge of the world merely knowledge of the way that the world seems to us? A number of philosophers have asked this kind of question, questioning some of the basic assumptions of science. Science relies on a basic assumption of realism. It supposes that the world is really some particular way, and that we really are able to determine how the world is by interacting with it, testing it, seeing it, perceiving it. On the other hand is anti-realism. Anti-realism comes in a number of forms because basically it's just the denial of realism. One form of anti-realism says that the world really just isn't any particular way. That form of realism is very difficult to articulate and defend, so we'll leave it here. But another form of anti-realism says, while the world is a particular way out there among, reality exists, we can never really determine what way the world actually is, what way reality actually is, the properties of reality by interacting with it. We never actually get beyond our mere perceptions of reality, the way things seem to us, and so we never actually get onto the real truth of reality. The famous philosopher Immanuel Kant believed that our minds have a particular shape. You can think of them in a way as like a kind of cookie cutter. And that shape forms the way we perceive the world. You can think of the world as an amalgam of, formless cookie dough that when pressed up against our minds, right, when it interacts with our minds, is formed in a particular way into a shape. Now, on this view, no matter how the world actually is out there, we can only ever understand the world in the shape that our mind molds it into. If our mind already comes in a particular shape, the way that the world is, our attempts at understanding the world, can only ever come through this intermediary shape. So to try and go beyond that, to try and know how the world is apart from the way that our mind actually shapes the world, is to attempt to know something that is literally beyond the limits of human knowledge as our mind limits that. So on Kant's view, there really isn't anything that we can truly know about reality other than that it exists because it's interacting with us. Right, we're in it. But we can know about how things seem to us, and we can come to understand ourselves and the world in this intermediary way, in this way in which our minds shape the world for us. Now, on this view, science, in a sense, is radically limited, but we can still do it. We just can't expect science to deliver the truth to us about reality. We can only expect science to deliver the truth about how reality seems to us. Now, in the wake of Kant, Kant didn't have access to some of the things that we think or believe are true now, partly due to some science that people have done. In particular, Kant didn't really have access to Darwinian explanations. Kant didn't really know about evolution, or the theory of evolution hadn't been fully formed yet. According to the theory of evolution, our minds are a product of the world, and the forces in the world have interacted with us, upon us, shaping us to be the particular ways that we are. So our mind, the shape of our mind, is actually a product of the world. And if there's a special connection between how the world is to begin with and how the world has shaped us, how we have become shaped by the world, then it may make sense to understand how we could come to know things about reality by using the tools that the world has literally shaped us to have. The world interacting upon us gave us perceptual capacities to track the ways that the world actually is. And those ways ultimately led to our being able to survive in the world along the lines of an evolutionary explanation. If this is the case, we may be in the clear. It may be that science really can get us at some bare bones cases of reality. We just have to recognize that there's lots of ways that things can go wrong because there are all of these intermediate factors. And this, in a way, I think makes sense in helping us to recognize the limitations of our own understanding and how long it's taken for science to kind of get up and running in the modern world. Science is a serious case of starts and stops, constantly putting forward hypotheses and coming to recognize that there's something that we totally didn't understand that we need to understand first before we can make any progress. Once we recognize that science assumes some form of basic realism about the world and takes this as a kind of article of faith, then we can be hopefully disabused a little bit or less tempted towards a lurking form of scientism. Scientism is the idea or the sort of, religious view of a form of irrational overconfidence in the power of science and scientific methods. We should take science surely can be the greatest knowledge-achieving tool that we have at our disposal, but that doesn't mean that we should worship it or think that it will solve everything. There are limits to science. Another aspect of science that's often overlooked is the fact that science actually is an endeavor that is fundamentally human, and it's fundamentally a human social practice. It's a way that we as humans come together in order to try and learn more about our world. All social practices have a sort of structure. They're motivated in different ways. There are aims or different kinds of goals. There are hierarchies. There's rules. There's checks and balances. And each of these kinds of things can in itself be corrupted in some way, shape, or form. Just take the idea of a goal or an aim. You can see that, certain scientists might be hired by, say, the big tobacco companies to investigate the connection between tobacco and cancer and come up with, various results that say that there is no connection. You might similarly think about pharmaceutical companies that have scientists working for them, where profits, in some sense, come first, and the truth might come second. These kinds of situations are just sort of, tip of the iceberg for how you might see the scientific practice actually become corrupted or problematic in some way. While science certainly aims at the truth, the social practice itself involves a number of different contenders, right? Things that you want to sort of achieve at the same time, or things that, can motivate people to act in certain ways within the scientific practice, like money, vanity, prestige, the ownership of like patents, one-upsmanship, right, and academic dishonesty. Each of these kinds of things can foil, what would be good science done well. There is, of course, hope. Ideally, science need not be beholden to the whims, trends, and downfalls of human endeavors and human social practices. We can ultimately distinguish between the way that scientific practice is, with all of its more difficult and problematic issues and setbacks, from the way that scientific practice should be. We can call this ideal science, or a perfected scientific practice. And this is something that, as a kind of something to be lauded and aimed at when doing science, we can, from thinking about it, parse a number of virtues in scientific practice at which we can aim. In the vein of an ideal science, scientists and philosophers have derived a sort of particular ideal scientific practice, or a method for which individuals can follow to, in a way, inductively determine the truth. And this has classically been called the scientific method, which hopefully everyone has heard of. And it involves, of course, observation, but observation under a general hypothesis or some kind of explanation for what's being observed. Given the general hypothesis or aim of the explanation or theory related to the observation, you can propose some kind of hypothesis, observe the world, try and determine whether or not the hypothesis is correct given the explanation proposed, and then test various hypotheses by checking for certain kinds of implications that will follow from the explanation and the initial observations. One crucial aspect of this is, of course, the construction of a hypothesis or explanation and the testing of that hypothesis. So there's a difference, and sort of it needs to be, parsed out between large and small hypotheses, right? So under a large kind of hypothesis, you have the general theory. The general theory is, in a sense, the grand explanation with wide scope of the entire scientific practice that's being undertaken, right? So like biology, you might be talking about like how the human body works or something like that. You've got a grand theory. Whereas then given the grand theory, if it's a good one, there are specific or specifiable predictions that can be gleaned from the theory, which can be in principle tested. That doesn't mean that they are always testable, right? Sometimes like a theory, has implications for things that are ultimately out of our reach because we're humans and we live on this planet, and things are only the size that we have available to us. But in principle, testability is very important. And then a small hypothesis, right? The small hypothesis is basically the suggestion that an experiment or that like a test will go a certain way on the basis of or assumption that the general theory is actually true. And then what can happen is once something has been tested, you can confirm or disconfirm the smaller hypothesis. If you confirm it, then great, right? That goes towards confirming the general theory. If you disconfirm the small hypothesis, well, then you have options. You can think, okay, this goes towards disconfirming the general theory, or you can, take the small hypothesis and say, like, this experiment, this test must have failed in some way. Let's run it again to see if we continue to get this result. A nice and easy-ish example here is that of Newton's laws of motion. So Newton had 3 laws of motion, right? The law of inertia, the law that force equals mass times acceleration, and the law of action and reaction. And these laws taken together constitute a general theory of motion. Now, the general theory itself provides us with specifiable predictions that are ultimately, in principle, measurable, right? So we have an object, O, of certain mass, moving at a certain speed, and then we can say that, if it has that mass and that speed and is accelerating at that speed, then it should have a particular force, right? And so we can think like, look, okay, we can assume in like a more small hypothesis format that Newton's laws are correct, and then determine, given the certain mass and speed, that a certain force will be, will register. However, we are actually running this experiment, and so you can test that hypothesis, you can deliver the results, and then you can check those results against the hypothesis in order to confirm or deny the hypothesis. The small hypotheses are taken together meant to help confirm or deny the general explanation or general theory that they are, part of or supposed to be part of. But the nature of sort of explanations and the nature of these general theories is quite complicated in philosophy. So there's lots of different kinds of explanations that are available, right? You can have like a mathematical explanation. Somebody could explain to you why a squared plus b squared equals c squared in the Pythagorean theorem, right? You could have a philosophical explanation, right? I can explain to you how conditional sentences work and necessary and sufficient conditions for why it is that being a cat it's necessary to be a mammal, and why being a cat it's sufficient for being a mammal, right? Then there's also causal explanations. Causal explanations are oftentimes basically like mechanistic. They say, well, when you do this thing over here, you wiggle this little knob here, it causes this other thing over here to move, right? And often, at the level of middle-sized dry goods, most mechanical explanations are just like, look, this thing touched this thing and it pushed it, and that all makes sense. But now, when working in science, we often are looking to causal explanations. But causal explanations themselves, like by themselves, aren't wholly adequate to give us the full picture. And that's because causal explanations rely on the nature of laws. So take, for instance, Newton's laws. So Newton's laws offer a framework that's like Newton's theory, right? He's got these 3 laws of motion. They offer a framework for understanding how massive objects interact with one another at various speeds, right? Using Newton's laws, we've actually been able to test certain things and come to discover stuff, right? So there's this example of the discovery of Neptune. The discovery of Neptune came from people observing the planet Uranus and observing that its as it moved around the sun, its orbit was actually off by a little bit, right? There were these weird perturbations in the orbit of Uranus. It was not moving exactly how Newton's theory predicted, right? And the reason, this is Newton's theory of gravity now, actually. Um, so one scientist basically thought, hey, this guy's name was Leverrier. He thought, well, okay, if, there's two options here. Either Newton's theory is just wrong, right? Or there's something else to be explained here. Maybe there's some other planet that's out there that's causing these perturbations in the orbit of Uranus. And basically what Leverrier was able to do there was to calculate where this new planet would have to be given the perturbations of Uranus using Newton's laws, the way that Newton's sort of math for gravity worked. He was able to calculate the location of this other planet, and he, postulated that it was there. And then once telescopes became powerful enough, somebody checked and was like, wow, yep, there's a planet there. And that's how we discovered Neptune, right? So this is sort of an interesting case for understanding how these kinds of explanations might go. However, Newton's laws themselves are incorrect for certain kinds of objects. So there's another example in which this exact same case the exact same, the formula didn't work out, right? And this is the example of Mercury. So Mercury, the closest planet to the sun, also doesn't orbit the sun in the way that Newton's laws predict. Newton's laws predict that it'll move one way, but it has a certain perturbation in the way that it moves around the sun. Scientists back in the day, thinking, oh, well, maybe it's something similar to what happened with Uranus and Neptune, postulated the existence of a planet that basically was closer to the sun than Mercury, but that for some reason we hadn't observed yet. They called this planet Vulcan, and if you're a Trekkie or anything like that, then you'll sort of recognize the name Vulcan. They postulated the existence of this planet in order to explain why Mercury moved in the way that it did. However, so this was their option, right? They had the option of either rejecting the Newtonian explanation and the Newtonian laws of gravity, or they could say, no, the Newtonian laws of gravity are correct for this causal explanation, right, of Mercury. But the thing is, Mercury is being affected by another planet, right? Another planet that we just haven't observed yet. They had those two options, and the ones that tried to postulate Vulcan were trying to explain it, and then they were trying to look for it, right, to see if they were correct. As it turns out, there was no Vulcan planet, and something else had to be done. What ultimately happened was that Newton's laws, Newton's theory, ended up giving way to Einstein's theory of relativity. Einstein's theory better explains things. It captures all of Newton's theory, that is, all of the things that Newton's theory sort of has. Einstein's theory also says those things. It also makes those predictions. It also explains those laws, right? In a way, Newton's theory, at least the correct parts of it, are incorporated into Einstein's theory. But Einstein's theory is more general in that it grasps other things. It also correctly predicts the orbit of Mercury. It predicts that things like that light is going to be bent around massive objects, which Newton's theory didn't have anything to say about. And Einstein's theory, of course, has been tested and confirmed many times. That doesn't mean that it's actually the ultimate and correct theory, right? It, just like Newton's theory, could be wrong in the end. it probably is in some specific ways, but maybe it can be augmented. But due to the success of Newton and Einstein's theories, it's become common practice nowadays to think of science and the scientific endeavor as a search for the laws of nature. And so you can think of Newton as having found what he thought were the laws of nature, and then, people tested them and they worked pretty well. But sometimes they broke down, right? Sometimes those laws broke down, particularly in the case of something like Neptune, or I mean, in the case of something like Mercury. Einstein comes in with a new theory, a new mathematical set of formula, and a new set of laws for how basically gravity works, and that's his theory of relativity. So on this view, and this has become common practice in certain circles of science, particularly those beholden to physics, right, both large and small. There are laws for which nature is, or to which nature is subject, right? And these laws are somehow put in place by, the structure of reality or the Big Bang or God, who knows, right? The laws of nature are just there somehow. And, this is why ultimately the causal explanations are sort of inadequate, right? Because we need, or we want, ultimately, some explanation of how and why the laws of nature are the way that they are, and how and why they came to be, if they came to be, right? If they didn't just exist eternally. But ultimately, everything is subject to these laws. And so then by observing things subject to these laws, we can then calculate or approximate these laws. So the thought is, what we're doing in science is seeing, observing how things interact with one another, using our mathematical abilities or our mathematical representations, this sort of way that we've come up with how to represent how things are in the world. We use that to basically note down, and we use that to help our observations in order to help confirm the hypotheses that we have, where the hypotheses that we have are ultimately sort of attempts at capturing or stating really what the law of nature really is that's out there, right? So one sort of mode of ideal scientific practice that has come to become very common, it follows basically this pattern, right? You propose, so like you're doing science, what you're going to do is you're going to propose a law of nature. That's your hypothesis. Then you're going to test instances, right, against that hypothesis to see whether or not that hypothesis is confirmed or denied, right? So suppose you have a law of how gravity works, right? Then you can test that by looking at the planets, right? If the planets, if maybe it gets the planets right in this solar system, but it doesn't get the planets right in another solar system, well then that's probably going to be like, well, okay, well maybe your theory, it's not like a law of nature, but maybe it helps explain, it just explains what's going on here in this in this galaxy, right? And this is actually something that happened with Einstein's theory. He has the theory of special relativity, which is for a specific case. And then he's got the theory of general relativity, which is supposed to apply universally. And then once you've got, you've tested your hypothesis, you're able to then confirm or deny the law as part of nature or not, hopefully. This then brings us to sort of our last form of argument that we're going to be looking at and thinking about in this class. And that really is the nature of abduction, the nature of inference to the best explanation. Inference to the best explanation is extremely common in scientific practice. In fact, you might think of it just as what science is, right? Science just is an attempt at inference to the best explanation, where you've got lots of data, lots of explanations, and lots of attempts to explain the data. And then you try basically to weed through all of these explanations, ultimately coming up with the best one. And then if you fail, then you continue to work on each explanation to see if it can better capture the data. Um, Einstein's theory of relativity is a sort of perfect case for how it eventually came to dominate Newton's theory, right? It came to dominate Newton's theory as a better explanation because it captured more information. It captured more information and got things correct, like in ways that Newton's theory just didn't. Of course, both theories had predictions. One theory ultimately made some incorrect predictions. And once it was recognized that, once you sort of see, right, you say you've got a theory and it makes a prediction, and then you see, oh wait, the prediction's not turning out right. Well, then you ultimately just have two options there, right? You've got the one option on the one hand, you can throw out the theory. And you could say, oh, well, I guess we got to go back to the drawing board. We got to come up with something new. Or you can say, no, the theory's still correct, right? The laws are still correct, I think. And something else has got to be going on in this particular case, right? Some other causal factor has got to be involved that we don't yet understand, or that we don't yet have, we don't know about. Now, of those two options, it's of course not worth throwing out a whole theory unless there's a contender theory as well, right? You don't want to throw out the baby with the bathwater sort of thing, right? If you don't have a correct theory, right? This is just one of those features of science, is that science continues to progress and get closer and closer to the truth. You don't throw out the whole theory if the theory is successful, in order to, like start anew if it's pretty successful, right? In this case, though, because Einstein's theory provides a better explanation of all the available data, it is one of those situations, right? It's one of those situations where, because there's this contender theory that actually does fully swamp the initial Newtonian theory, then you can sort of throw out the Newtonian theory in favor of the Einsteinian theory. This is what's often called a paradigm shift in science, as coined by the sort of philosopher and sociologist of science, Thomas Kuhn. The idea here being that there's different ways that science kind of proceeds. Sometimes science proceeds very like piecemeal in a normal way, where you're just testing the laws and you're coming up with, confirming instances by doing experiments. And other times, whole new theories need to be come up with in order to replace earlier theories, by hopefully covering more ground than those theories. Abduction is, in a way, like induction and deduction, insofar as there are rules that we need to follow when making these kinds of inferences. Sadly, these rules are not nearly as rigorous or formalized as looking for validity or cogency, right? We don't have all of the fancy statistical devices for abduction. Similarly, we don't have formal methods of deduction. However, there are criteria for finding good abductive arguments. But those criteria are, in a way, looser or more open to interpretation. Or maybe not interpretation as much as they're more open to being weighed against one another. And sometimes you might think that one criteria is more weighty than another in a particular case, and that might lead you to think that one kind of theory is ultimately a better explanation. One kind of explanation is a better explanation than another, simply because it does better in one vein than on one criteria than the other. Sometimes, ultimately, no theory wins out when it comes to these inferences to the best explanation. In particular, this happens a lot in philosophy. There are cases in which there are competing theories that are kind of on par when it comes to these criteria, but we'll come back to that. Usually in science, if no theory wins out, that just goes to show that we need to do more experimentation, or we need to allow scientific technology to advance, or something like that, before we will be able to actually see and test these theories. And the criteria of adequacy for abductive inference are thus: testability, fruitfulness, scope, simplicity and conservatism. And the rest of this lecture is just going to be explaining what those are. The first criteria for a good abductive inference is going to be testability. A theory is ultimately testable if you can offer a hypothesis and then set some sort of standard for falsifiability under which the hypothesis can be shown to be incorrect. If the hypothesis isn't shown to be incorrect, then of course that's a version of a verification of the theory, but only piecemeal, right? It doesn't show that the theory is true, it just shows that the theory is not false. The easier it is to sort of show a theory to be false, that is, the more ways by which the hypothesis can kind of go wrong, the more scientifically commendable the hypothesis, in a sense. If the theory is difficult to show to be wrong, then there may be an unscientific reason for that. Falsifiability in principle is basically just that in principle it's possible to find evidence that could show the hypothesis is false. And ultimately, a number of theories simply are unscientific because they're not falsifiable. Religious theories tend to be this way, right? Like that miracles occur, or theories about the existence of God. Similarly, political theories, right? Like, so Marxism is a classic theory that ultimately doesn't seem to actually be falsifiable because it doesn't make enough predictions, or when its predictions are shown false, there's always issues in the background that can be fiddled with, that you can say, oh, really, this didn't show that this was false because the background conditions weren't just right. In each of these cases, there's just not the right kinds of testability in place to show that the theory is falsifiable, and so the theory is in some way unscientific. Some theories are also currently only theoretical, and so they're in a sense unfalsifiable because they are currently untestable. So this is the case with string theory. If you haven't heard of string theory, it's a theory of basically the subatomic particles of the world, right? The fundamental particles, if they are little basically circular strings, they can vibrate in certain ways. And then the idea there is that there's like a mathematical theory of how the universe could exist in the way that it does. But there's no current way. I mean, the string theory is a theory. It's basically a mathematical theory of how the universe operates. But there's no way of testing it because we just don't have the ability to, get to that level of minuteness. And so the theory is, in a sense, only theoretical at this point because it's untestable. If a theory is not testable, then ultimately, what reason do we have for believing it in the face of other theories that concern the same topic, especially if those other theories are testable? The second criteria for determining an inference to the best explanation is the fruitfulness of a theory. A fruitful theory can be seen or used to generate and try to confirm novel hypotheses, right? So novel hypotheses are basically just new hypotheses where you take the general theory and use it to construct some new claim that then you can test. Something here like Newton's law of motion is extremely fruitful because the general formula allows you to plug in sort of like mass and acceleration and determine the force. Or similarly, you can sort of do it with any of the two, right? If you have force and mass, you can figure out the acceleration. If you have force and speed, you can figure out the mass, etc. And the fruitfulness of this, at least for the regular size stuff, right, is extreme because we can show all these things. Now, of course, Newton's theory of gravity ultimately was fruitful up to a point, and it didn't, work all the way, but still, the theory is extremely fruitful because you can kind of do this with it. Theories that don't successfully generate novel hypotheses are often kind of constantly trying to explain away extraneous data, right? And these explanations are called ad hoc explanations, or explanations just in this case. Terribly unfruitful theories usually involve so many ad hoc claims that it's hard to really argue against them because there's always some sort of alternative response. Uh, this happens a lot when arguing with like conspiracy theorists. A good way to test basically these theories for fruitfulness or unfruitful theories, is to ask what a theory predicts and what it predicts we'll find if we are able to look in certain places, we're able to test. And how many caveats the theory is going to sort of lay bare if the prediction fails, right? So remember, like a good testable theory has lots of ways it can go wrong, and then lots of ways you can show the hypothesis to be wrong. An unfruitful theory in this case is going to be one where the hypothesis has a bunch of caveats that ultimately don't show the theory to be wrong, right? When the test goes bad for the theory. A third aspect of inference of the best explanation or the criteria is the scope of the theory. Now, the scope of the theory determines sort of how broad the theory is or how much it applies to. And so, of course, a theory with the broadest scope that applies to everything is the best kind of theory, in a sense. So, for instance, take the study of biology. The study of biology currently, for obvious reasons, only focuses on terrestrial living creatures, right? It's broad enough to cover everything that lives on Earth and maybe some of the like microbial stuff that we found in space, but it doesn't offer knowledge or understanding that might apply to alien species, the biology of an alien species, right? And one day maybe we'll find alien species and we'll need to understand how they're, alive. A broader theory of biology, one that takes into account different evolutionary chains, different kinds of living creature, would have wider scope, right? And would try to locate principles that may apply across different kinds of living things, not just biologically living things, or Earth bio, right, living things, but aliens as well. Sometimes the theory scope ultimately outstrips it, though, in other areas, right? So string theory, like I was saying earlier, is this theory that's trying to have the widest scope possible, right? It's trying to explain everything, all the way down to the fundamental particles. However, while the scope is broad, the theory itself is untestable. So the theory, so the theory needs to be thrown out in that sense, right? It's problematic. So scope really only matters in cases where the theory is sort of already testable and already has fruit. So in this case, right, the Einsteinian theory of relativity over Newton's theory of gravity is a great example because the scope so Einstein had the two theories, right? He has the special relativity theory, which has to do with specific cases, particularly focusing on the nearby universe to us, and then the general theory of relativity, which is supposed to apply to everything. And that, his theory covers all of Newton's theory. That is, it takes over the same scope as Newton's theory. It applies to all the things Newton's theory applies to and more. And so that's why it's successful when it comes to scope. Criteria, simplicity is another criteria, the fourth one here. And simplicity is rather interesting. So there's kind of two different veins of simplicity. There's the kind of Occam's razor vein, and then there's the theories that are more aesthetically pleasing in a way vein. So first, a simpler theory is a theory that postulates sort of less. It gives you less machinery, it gives you less things to explain. It gives you less like objects, right? So I don't know. Less things to take as fundamental to the theory, right? Just less things to take on faith in a way. And one example here is this is like a classic kind of fun example, the phlogiston theory of fire. So back in the 1600s, people didn't understand how fire worked, right? if you think about it, fire is kind of crazy, right? Like, what is it about certain things that makes them flammable while other things aren't flammable? And why is it that when you burn something, which basically like just looks like, I don't know, hot air, how come when you burn certain things, all of a sudden they become like smaller, right? And they come to weigh less? Well, ultimately, one guy or a series of scientists postulated the existence of this thing called phlogiston. And the idea of phlogiston was that inside things that are flammable, there's lots of phlogiston, and inside things that are not flammable, there's no phlogiston. Then the phlogiston theory was that, well, okay, so phlogiston is the thing that burns, and the thing that gets released into the air when when the thing is burning, and when the thing is done burning, then all the phlogiston's in the air and there's no phlogiston left in the resulting thing. There was a problem though with this theory, and in part of why it's not terribly simple. I mean, it seems like it's a straightforward theory, right? Like, but ultimately the theory is not terribly simple because it ends up having to postulate a bunch of weird things. So here's one case. Certain kinds of metal, when they burn, don't lose weight. They actually gain weight. And we now know about this. It's called oxidation. Basically, things grab oxygen atoms out of the air when they're burning, and so they can actually become heavier. But the phlogiston theory couldn't really explain this. So proponents of the phlogiston theory had to postulate the existence of negative weight. What the heck is negative weight? Well, negative weight is this thing that phlogiston has when it is had by certain kinds of objects, right? So when the metal has the phlogiston, it has negative weight, which means that the metal is lighter than it would be if the phlogiston weren't there, right? And so the phlogiston, once the phlogiston burns off, the thing becomes heavier. Now, the postulation of negative weight is just, it's almost ad hoc, and it's very complicated, and it makes the theory much less simple. It makes the theory much more unwieldy. If you have to postulate, well, okay, sometimes in things phlogiston adds weight, and sometimes things phlogiston adds negative weight. So when it comes to Occam's razoring things, your theories, you don't want to postulate anything beyond explanatory necessity. That is, as long as everything is explained that's relevant to being explained, you don't need to postulate anything beyond that. So some kinds of explanations do postulate too many things, and if they're unnecessary to, if those things are unnecessary to postulate in order to explain everything, then just don't. On the other hand, besides the sort of Occam's razor understanding of simplicity, there's the kind of beautiful theory understanding of simplicity. And on this view, it just sort of works out that oftentimes theories that are sort of more mathematically elegant, that is, theories that have kind of not necessarily easier math, but math that works out really well, often involve fewer features, and so just kind of fall into the Occam's razor category, but they just kind of, the theory kind of comes together. It jives well with itself and with other things. And these kind of beautiful theories, right, like you can usually like explain them more simply, or you can even just like show them more simply. And one sort of obvious case here is the planetary orbits, right? So heliocentric theory of the solar system versus the geocentric theory of the solar system. The Earth rotated, all the planets rotating around the sun in circles, or like ovals, much more explanatorily satisfying than the weirdness that would be every planet and the sun rotating around the Earth and making like crazy loops. Because sometimes when we look out at, you've probably heard of Mercury being in retrograde. That means that, at one point when you're looking at Mercury, following it in the sky, it's going one way, and then all of a sudden it turns and goes back. It goes the other way. Here's a little example of what, the difference is, right? The heliocentric theory is simply more beautiful, right? More aesthetically pleasing in a sense. And that's because it's simpler. There's a lot less nonsense going on, whereas the geocentric theory requires all of this nonsense in order to explain it. And so there's just something about this kind of the background conditions here that seems to suggest heliocentrism over geocentrism because of its simplicity. The final criteria of a good inference to the best explanation is conservatism. And this consists of consistency and coherence. A more conservative theory is going to be consistent with our background beliefs, and that requires us to give up fewer things that we already think or believe, or fewer things that are already sort of established by the science that we trust. The more a theory ultimately coheres internally and with other theories that we find acceptable, the better. Sometimes theories are, in a way, conservative by luck because they introduce you to a new set of information that doesn't really have anything to do with your background beliefs. Like when you just come across a wholly new theory, or some scientist has been working on something that's totally brand spanking new. Other times theories are extremely unconservative in certain ways and then, eventually come to be fruitful or accepted. Or at least often these seem to be so because they seemingly conflict with certain background assumptions that we have generally. One of the examples of this, something that's caused a lot of confusion and difficulty over the last century, is quantum mechanics. Quantum mechanics, of course, studies the subatomic particles and this sort of statistical nature of the universe. And some of the features or experimental data of quantum mechanics seem to conflict with things like logic, right? There's the question of whether or not a quantum mechanical, whether or not things at the quantum mechanical level are particles or waves. There's this whole notion of something being in a superposition, being in two states at once, right? The question of whether or not Schrodinger's cat is dead or alive, or both at the same time, right? Can it be both? These kinds of things seem to create problems with our beliefs. There are workarounds for ultimately accepting some of these seeming problems, but people have a lot of people have thrown shade at quantum mechanics because these things seem unbelievable. Another instance from quantum mechanics is the existence of this thing called quantum entanglement, where quantum entangled particles can be very far apart from one another, but something that acts on one will act on the other, right? And there doesn't seem to be any sort of like causal linkage between these two particles, but once they are entangled, it seems like action at a distance is possible. That is, like, you fiddle with one and the other one moves, and it's like, wait a minute, that doesn't seem right. That seems like magic. Wrapping up this lecture, it's ultimately healthy to be skeptical of new scientific results, ones that have not been replicated and proven over and over again. We shouldn't outright reject the results, but we shouldn't, and we shouldn't really give into our confirmation bias. That is, like, you shouldn't have a presupposed idea and then just go out looking for things that reinforce your presupposed position. It's best to just sort of be generally be generally questionable about the scientific result and think, okay, this is interesting, but is this true? And we need more. We need to do more in order to show that it's true. There's lots of issues within science as it's done, as social practice, and often within the way that science is communicated to the general public. And so it's helpful to kind of distinguish between the different kinds of sciences that are what we might think of as more hard and more soft. So highly confirmed hard sciences at this point are things like physics, chemistry, and and parts of biology, right? So at least the physics of things like atoms and electrons, protons, and neutrons, we have that pretty squared away. The more fundamental stuff, the subatomic particle stuff, definitely we don't have as squared away. But at the level of the atom, the physics is pretty good. Similarly, at the level of like planetary movements and stuff like that, right? We know what's going on in the universe. Chemistry is pretty much the same. We know a lot about the different chemicals. We know a lot about the different reactions between chemicals, right, between different kinds of atomic structure. And then basic biology, right, like biochemistry. There's a lot there that is, completely backed up. There are, of course, like newfangled things that we find all the time, and there's lots still to be done in biology, learning about all kinds of different kinds of creatures and how certain biological systems actually function. I think recently there was an entirely new system found inside the human body that people didn't really believe was there for a long time. I mean, like there's still a lot open there, but the sciences themselves are overly confirmed often, right? Where there's a lot less well-confirmed sciences that are more difficult in the first place. So experimental psychology, where oftentimes people are basically doing certain kinds of psychology while also scanning the brain. So it's like neurology or neuropsychology or something like that. Pharmacology, right? So how certain drugs affect the body in certain ways. And nutrition science is just like totally whack, right? I feel like every few months you see an article that says like eggs are good for you, and then one that says eggs are bad for you, and right. The science there is definitely worth being skeptical about. There are certain things that are well known, right, about like calories and how if you ingest more calories you will gain weight, and how if you ingest less calories you will lose weight. But a lot of the kinds of like things about gut science and all of that are not to say that they're bunk, they're just not very well confirmed. And so there's lots of different other things that could be going on. And so the claims of these kinds of sciences are to be trusted less in an outright way. And then there's the soft, like the actually soft sciences, right? So these are things like anthropology, sociology, classic psychology, and political science, where these deal in thinking about the behaviors of humans, right? So there's a subfield of like anthropology that's like called evolutionary anthropology, which suggests why certain kinds of traits may have evolved given certain kinds of evolutionary needs for our survival in the past. Now, this kind of theorizing is very interesting and fun to think about, but it's also very difficult to prove. And because it's very difficult to prove, it's very difficult to test, to experiment on, and because of that, it's just very hard to say without doubting at least somewhat some of the results of these theories. Similarly, psychology, right? Like just generally trying to understand somebody's somebody's actions or feelings on the basis of assuming that they have an Oedipus complex, or that they went through some sort of childhood trauma and that's why they are so angry now. Like these kinds of things are much more difficult to prove, even though we are still sort of on board with many of these theories. They definitely give us insights, while we shouldn't sort of trust them in the same way that we can trust physics, chemistry, and bio. A healthy skepticism is, of course, healthy, right? Especially within the realm of the soft sciences. It best to be wary. Currently there's a replicability crisis going on in specifically social psychology, where and this involves many of the things that we covered in the bias section of this class already. Many of the experimental results that that have been, shown in the past have been casting it out because the results are unable to be replicated. Like, people try to replicate them by recreating the experiments, and the results just don't come up the same. And there's lots of reasons for the difficulty of replicability in these kinds of sciences. And coming up with like facts in the soft sciences is hard to begin with, as it's much harder to sort of do the adequate experiments and take all of the possible extraneous conditions into consideration. Similarly, there's just issues with the way that the social practice of these kinds of sciences is done, right? There's rarely as much funding in sociology and psychology departments for replicating an experiment that somebody else has already done, because it's just not as interesting or sexy in a way. Another issue is that, like, in academic environments, there's this thing called publish or perish, which is too bad. It basically just means if you don't publish your results, and you don't get, like, then you're not going to keep your job. You're going to not get tenure or something like that. And this attitude drives people to publish things without always adequately pursuing due diligence. They publish things that maybe they're shoddier than they should be. I think it's also just a good idea to be skeptical of anything that's trendy. There's lots of science journalism that goes out, and you've probably heard it in podcasts and read it in news articles, or read like Malcolm Gladwell's books or something like that. A lot of these kinds of things are more fringy than you'd think, in the sense that they just aren't fully replicated. We haven't sat with them long enough to know what the real truths are. And these kinds of, the exciting things are what get blasted out by the journalists, because that's the stuff that sells. That's the stuff that people want to hear about. And the issue there is just that just because people want to hear about it doesn't mean that it's actually true, or doesn't mean that the science is really there to back it up. So it's worthwhile to ultimately be generally skeptical of anything that you find lots of recent articles about, because the trendiness of the topic shouldn't actually be any kind of guide to whether or not the science is good.